All right, so in this video, we're going to prove that if f of x is an odd function, then the integral from negative r to r of f of x dx equals 0. So let's first just look at an example of this fact. For instance, let's say that f of x equals x cubed, and r is equal to positive 2. Okay, so then our integral becomes the integral from negative 2 to 2 of x cubed dx. So let's just evaluate this integral real quick. We know that we can use the reverse power rule to get x to the fourth over 4. And then plugging in our bounds of integration, we get, and this results in 0, right? So this integral results in 0. So this particular instance satisfies what we expect it to satisfy, right? This integral should equal 0, and we find out that this particular instance actually does result in 0. But what I want to look at is what this integral looks like geometrically. Let's draw a graph of what this integral looks like. So this right here is what our definite integral looks like graphically. And notice that these two areas appear to be equal to each other. And in fact, they are. The only difference is that this area is below the x-axis, this area is above the x-axis. But if you recall, when it comes to definite integrals, area below the x-axis is negative, area above the x-axis is positive. As a result, these areas cancel out. They cancel each other out so that the definite integral results in 0. And geometrically, it makes sense why this would happen. We know that x cubed is an odd function. It turns out what that means is that for every point x comma y that exists on x cubed, the point negative x comma negative y will also exist on x cubed. For instance, we know that the point 2 comma 8 is on x cubed. Therefore, the point negative 2 comma negative 8 is also on x cubed. And geometrically, you can imagine this point is here, therefore this point is here. This point is here, therefore this point is here, about, and so on. We can imagine that total area that we accumulate here and here should cancel each other out. And it's all because we're dealing with an odd function. That's really the whole idea. And so we should expect the same sort of area cancellation to happen for any odd function, right? The integral should result in 0. So how do we show that this integral is equal to 0 for any odd function? That's our next goal. So how do we actually show that this integral is equal to 0? Well, because f of x is an odd function, by definition, that means that f of x is equal to the negative of f of negative x. And as a result, we can replace f of x with negative f of negative x. Okay, so then what can we do from here? Well, it turns out what we're going to do here is we're going to perform a u substitution. We're going to set u equal to negative x. And therefore du is equal to negative dx. So really, what we're going to do here is we are going to replace the negative x with u, and we're going to replace the negative dx with du. If we do that, we will get this. But we still have to take care of our bounds of integration. And to determine our new bounds of integration, we're going to use the relationship between u and x. Notice that if x equals negative r, then u is equal to the negative of negative r, which means u equals positive r. So that is what our first bound of integration becomes. As for our second bound of integration, if x equals r, then u is equal to negative r. So we get negative r for our second round of integration. So this is what our integral becomes, right? We have converted our integral in terms of x to our integral in terms of u. But here's what's really interesting about definite integrals. When it comes to definite integrals, it doesn't matter what we call our variable. For instance, consider these two definite integrals. Consider these two definite integrals. Is there any difference between these two definite integrals? I mean, maybe. Right here we have the variable x, but right here we have the variable u. But that doesn't matter. The numerical result of these two integrals will still be exactly the same thing. And you could also see what this would look like graphically. As you can see, this area is equal to this area. The only difference is that here we're calling our variable x, here we're calling our variable u, but that doesn't change the numerical result of the area we have, right? These two definite integrals have the exact same numerical value. And as a result, it doesn't matter what we call our variable, which means that we can change u back to x. Just like that, right? The numerical result of our definite integral will be the same no matter what we call our variable. I know it's a little weird because we said u equals negative x. So you might be thinking, well, shouldn't we be replacing u with negative x? But that's not really the idea. The idea is that definite integrals don't care what we call our variable. And so that's really the whole idea. So now that we have this, what we're going to do is we're going to move back up here. Another property of definite integrals is that if we swap the bounds of integration, it negates the integral. As a result, this is what we get. But notice what we have discovered is that our original integral is equal to the negative of itself. Right? The original integral equals the negative of itself. And so what this means is, if we let our original integral equal some number I, what this means is that I is equal to negative I. And so what we can do from here is we can add I to both sides. We get 2I equals 0. But then if we divide 2 on both sides, we get that I must equal 0. And since I is equal to 0 and I is equal to our original integral, that means that our original integral is equal to 0. And so we have proven exactly what we wanted to prove. Yeah, that's pretty much it for this video.